Long short-term memory neural network is considered as a powerful solution to vanishing and exploding gradient problem of simple neural network. In the mid-90s, Steph and Joren, the German researchers, proposed the long short-term memory neural network as a solution to the vanishing gradient problem. The LSTM network can preserve the gradient along the path of backpropagation through time and layers. This maintains a more consistent gradient while backpropagation is done. The neural network can continue learning over many time steps. The cell state can transfer information from the earliest time steps to all the way to the end of the sequence gene. It can carry relevant information throughout the processing of the sequence. It can mitigate the problem of short-term memory. LSTM gates. LSTM cell uses the gates to regulate the flow of information moving along the path of processing the sequence chain. There are three gates for get, input, and output. In the LSTM cell, each with one sigmoid activation function. Each gate is a neural network that can learn to determine what information should be relevant or significant and then be used. Each gate can learn to decide during the training on what information to keep because it is relevant and which information to forget because it is insignificant. In part 5, we have designed an LSTM. This slide shows the same and the architecture and configuration of the LSTM model designed for time series data analysis. The model comprises three stacked LSTM layers, each with 50 neurons, utilizing the ReLU activation function. The return sequence is set to true, which enables stacking and ensure sequence outputs are propagated. Two dropout layers, each with 20% regularization to help mitigate overfitting. The input sequence length is set to 60 with a batch size of 32 and 100 epochs for training. The table details the model layers, output shapes, and parameter counts, illustrating the complexity of each layer. The design captures temporal dependencies effectively, demonstrating the length of LSTM in the time series forecasting. Here we see the loss function plot, which demonstrate the model's learning progress over 100 training epochs. The y-axis represents the loss value, while the x-axis denotes the number of epochs. A sharp decrease in the loss is observed at the beginning, indicating rapid learning. The loss then stabilizes, signifying convergence to an optimal solution. This steady decline and evenful plateau reflect effective training and minimal overfitting. Such insights are vital for assessing model performance and ensuring it generalizes well to unseen data. Here we can see the forecasted data plot, showcasing predicted trends over a specific range. The x-axis represents the time or sequence, while the y-axis indicates the forecasted values. The curve highlights key patterns, including an initial sharp increase, peaking around 520, followed by a cyclical fluctuation. These insights are crucial for understanding potential feature, behavior, and making informed decisions based on predicted trends. The plot can be used to validate forecasting model accuracy and identify trends such as growth, decline, or stabilization in observed data. Here, we can see the actual data represented in a plot. This slide illustrates the actual and the forecasted data for stock prices from 2022 to 2024. The blue line represents the historical close price, capturing past fluctuations and trends, while the orange line indicates the forecasted price, projecting future movements. The model effectively captures the historical data trend and predicts a stabilization in the near future. Such analysis is instrumental in identifying potential market behavior, aiding in strategic financial planning and investment decisions. The comparison between actual and forecasted data validates the model's accuracy and reliability for predicting future trends. In part 5, we have redesigned the neural network to in an attempt to improve the performance of the model. This slide discusses the redesign of the neural network focusing on stacked long short-term memory architecture. The network consists of 4 LSTM layers, each with 60 neurons and ReLU activation. To enable stacking, the written sequence is set to true uh, and with regularization is incorporated through 3 dropout layers applied after each LSTM layer with a 20% dropout rate to prevent overfitting as done in the previous model. The model processes input sequences of length 60 with a batch size of 32 for training. It is trained over 100 epochs, balancing computational efficiency and accuracy. The design enhances the model's performance on sequence-based tasks. Here we can see the loss value. This plot represents the training loss curve for the redesigned neural network. The graph illustrates the decrease in the loss value over 100 training epochs. Initially, the loss starts at a high value, reflecting the model's poor initial predictions, however, rapidly decreases during the early epochs, indicating effective learning and optimization of the model's parameters. Beyond epoch 20, the loss stabilizes with minor fluctuation, suggesting convergence and a reduced rate of improvement. The consistent decline in loss highlights the model's ability to generalize well to the training data. This curve is a key indicator of the network's training performance. Forecasted data. Here, we can see the forecasted data produced by the redesigned neural network. The graph shows the model's ability to predict trends and fluctuations within the dataset. The x-axis represents the sequence of the time steps, while the y-axis indicates the predicted values. The curve captures the significant decline followed by a sharp rise, reflecting the variability in the underlying patterns. The smoothness of the curve suggests that the model's effective handling of data without overfitting or noise amplification. These results demonstrate the model's applicability in forecasting scenarios, providing insights into temporal dynamics for informed decision making. Actual and forecasted data. This slide shows the forecasted data produced by the redesigned neural network. The graph shows the model's ability to predict trends and fluctuations within the dataset. The x-axis represents the sequence or the time steps, while y-axis indicates the predicted values. The curve captures the significant decline followed by a sharp rise, reflecting the variability in the underlying patterns. The curve smoothens of the smoothness of the curve suggests that model effective handling of data without overfitting or noise amplifications. These results demonstrate the model's applicability in forecasting scenarios, providing insights into temporal dynamic of informed making of for making informed decisions.